Hello everyone and welcome back to 𝗕cie𝗶𝘁𝗵, broadcast from SobolevSpaces. In this video I introduce marginal contrasts as a vehicle for calculating treatment effects. First we'll take a look at marginal means and marginal risks. Then you will learn about the difference between conditional and marginal contrasts. Make sure you watch until the end. You will find out why contrast in experiments are different from contrast in observational studies. As always, I have a PDF with extra material for this video. Check out the link in the description and it will be sent to you. Now let's combine two ideas, population effect and potential outcomes. We begin with the average treatment effect. It's the difference between the expected value of potential outcomes with and without treatment. As usual, I'll let treatment variable x represent two groups. Treatment group is coded by 1 and the control group is 0. And let outcome y be a continuous variable this time. For instance, weight at birth in grams. What if unit u gets treatment 1? Then y1 of u is the value that would be observed. y0 of u would be observed for treatment 0. The effect of treatment 1 relative to treatment 0 in unit u is the difference between y1 and y0. The average effect in the population of units is the expected value of the individual effects. This is the same as the difference between the expected outcomes among all treated with treatment 1 and among all treated with treatment 0. It follows from the linearity of the expectation. Quantities on the left side are parameters of the population distribution. Now, this is important. The average effect is the difference between these two parameters. To emphasize this, I will introduce a new notation. Boldface capital E superscript 1 denotes the expected outcome for treatment 1, and E superscript 0 is the expected outcome for control treatment. Notice that the superscripts 0 and 1 refer to treatments that every unit receives. 1 is an index here, not a power, so is not. For short, I say E1 and E0. In the treatment effect literature, these expectations of potential outcomes are called marginal, unconditional means. No other variables are taken into account. They are calculated over all units, not just in treatment groups. Let's confirm that for a binary outcome, the average effect is a difference between marginal risks. This time, we consider an indicator variable y. It takes on 1 for the outcome occurrence and 0 otherwise. When there are two treatments, there are two potential outcomes for each individual unit. Individual treatment effect is a difference between these potential outcomes. The average effect in population of units is the expected value of individual effects. We can express this in a different way, as a difference between the expected outcomes for all treated and for all untreated units, because the expectation is a linear function. It sounds like I am repeating myself, almost, but the expected value of a binary variable is the probability that it takes value 1. Therefore, the average effect is a difference between marginal outcome probabilities, marginal risk in short. In the context of potential outcomes, marginal risks refer to the probability that outcome takes value 1 in a population of all treated units, and then separately among all untreated units. Again, these risks are unconditional probabilities. No other variable are taken into account. Now, these probabilities are population parameters as well. They are the expected proportion of units that would have developed outcome 1 if all units were to receive a certain treatment. They summarize at a population level what the outcome would be in the same patients under different treatments. Our notation here reflects that we are dealing with the entire population under two treatments, boldface capital P1 and P0. Average treatment effect is the difference between these two population parameters. We use the expected proportion of units with the outcome occurrence to assess whether there is a difference between two situations. One is all units undergo treatment of interest, and the other, all units from the same population get control treatment. we are trying to see how the outcome of interest compares to what would have happened to the same units under alternative treatment. Now that we've spent some time on marginal risk, let's revisit conditional contrast. The key concept we start with is the target population. It's what we have in mind when we draw causal conclusions. It could be a theoretical population of all patients with a certain condition, or the population of hospitals, catchment area, or frontline healthcare workers during an epidemic. The study population, on the other hand, is made up of treatment groups. Marginal contrasts compare potential outcomes of treatments as if they were applied to the entire population. We contrast these two marginal risks. P1, the outcome probability when all units are treated, and P0, had they not received the treatment or had they received a different treatment. The same population of units is considered among treated and untreated. Conditional contrast, on the other hand, compare outcomes observed in the treatment groups. Some study units underwent one treatment and some other units had control treatment. We contrast conditional outcome probabilities given treatment being 1 or 0. Let's review conditional contrast from randomized trials. I'll use a mosaic plot. The unit square depicts a study population. Vertical line divides the square in two parts. They show treatment groups. Participants are randomly assigned to treatments. One half is the treatment group and one half is the control group. Let's say 2/3 of the treatment group and 2/9 of the control group have the outcome. This plot shows a taller rectangle on the left. Probability that y is 1 given x is 1 is bigger than when it's 0. This is a positive association between treatment and outcome. Here is what we can conclude. Random assignment makes treatment groups as similar as possible in all respects, except treatment, of course. If true, then the proportion of units with the outcome in the treated should be the same in the control group had it been treated. We reason that after randomization, the outcome probability in treated represents the marginal probability for the entire population if they were treated. The same conclusions can be made for the control group. Its outcome probability represents the marginal probability for the population without treatment. That's why we use this conditional contrast and declare the effect of treatment is about 44%, even though it compares outcomes from the treatment groups. In experiments, conditional contrasts give us unbiased treatment effects because they coincide with marginal contrasts. This may be not the case with treatments in observational studies. We cannot ignore potentially uneven distribution of outcome determinants across treatment groups, and therefore we may not be comparing like with like. As a result, conditional contrast from observational studies may not give us unbiased treatment effect. Let's picture again a study population made up of two groups, now with observed treatments. Assume that 1/4 of participants is in a treatment group and 3/4 are in a control groups. Let's say 2/3 of the treatment group and 2/9 of the control group have the outcome. Again, we see a positive association between treatment and outcome. And yet, we are comparing outcomes of observed treatments, not the randomized ones. We can no longer assume the study groups are similar in all respects except treatment. Just like in trials, some units are treated and others are not. But we can no longer assume that either group is representative of the entire population. Therefore, we can't reason that the proportion of outcomes in treated would be the same in the control group had it been treated. And that's a crucial assumption for group comparability. There you have it. We cannot use the outcome probability in treated to represent the entire population had it been treated. The same is true about the outcome probability after no treatment. We cannot use it for the entire population if it were without treatment. That's why this conditional contrast, 4 out of 9, doesn't help us in comparing the marginal risks. In today's lesson, we combined two ideas: population level effect and potential outcomes. My main message is that the average treatment effect equals the difference between the expected potential outcomes with and without treatment. The treatment effects literature calls these expectations marginal means. They summarize at a population level what the outcomes would be in the same patients under different treatments. I hope you come away with understanding the difference between conditional and marginal contrasts. In conditional contrasts, the outcome probabilities come from treatment groups. Some units are treated, others remain untreated. In marginal contrasts, treated and untreated groups are made up of the same units. You watched another episode of Causality with Boris. Keep on watching.